Okay, so parallel circuit, so we'll go to page 413. Okay, actually, we're just gonna go ahead. Well, let's go to page 414. Go to page 414, and you can see there on the very top that there is a diagram there that has R1 through R5, and it's connected by a battery there. Circuits. So in parallel, so where they have this and you have a battery, you have 1, 2, 3, 4, 5, connected this way. So let's say that I am the electrical current, I'm running out of the battery, right? And I come to this node. This node here is the same as this node, this node, this node, this node, right? Why are they the same?
They're all positive.
No. There's nothing in between here, right? All there is wires, right? So there's nothing that impedes really from here to here to here to here to here. They're all the same. They're all the same nodes. In other words, you can look at it as I have a battery. It goes like this, and it's going to come out and it's going to branch out like this. This is the same thing here, right? Coming out like that. Yeah.
So is it giving, this may be really dumb question. So if the battery has a certain amount, is it giving all of it an equal amount, or is it only giving the first one that amount and then it transfers to the second?
No, so the voltage drop across here is the same as the voltage drop across here. Again, because there's nothing in between here, they're just wires, right? So if I have 18 volts here, that 18 volts is going to be across here, which is going to be across here, 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 here. And that is the magic of this parallel circuit.
So they all have 18 volts?
Correct.
Okay.
So if this was 12 volts, okay, I have 12 volts across here, 12 volts across here, across here, across here. So when I come to here, if I'm an electron and I come to, okay, an electron, I'm actually going to go this way, right? But if I'm the current and I come to here, I actually have a choice to go here, 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 or here. Okay, in other words, the current flow through here is going to be different from here to here to here to here. Okay, so let's go ahead and actually just jump right into the example. If I go into the example, I think I have 3. It's a 3-pronged one. Let's just go ahead and do the example. If you do the example, the voltage is 9 volts. So I have 9 volts here, and I have a 3 ohm resistor, and I have 7 and 9. 9 ohms and 7 ohms here, right? Okay. Since I know that the voltage drop across here is 9 volts, okay, and what I'm interested in is the current here, right? I'm interested in the current. So then we'll call this I1, we'll call this I2, we'll call this I3, okay? The equation on the top of 414 tells me that the total resistance here is going to be 1. This is the total resistance. I'm going to find that out by solving this. Okay, I'm going to find it out by solving this. Okay. So how would I do this? I'm going to go ahead and say this is going to be 63 over 21, 9, common denominator, very hard math here, right? Common denominator, 3, 7, and 9 is 63. Add them together, I get 37 over 63. This is 1 over R total. So R total is going to be what? 63 over 37. I'll just flip both sides over, right? Flip both sides over. And this is my total resistance, which means, and this gives me the total current flowing through here, right? Because by Kirchhoff's law, I total is equal to I1 plus I2 plus I3 in this node because they go in and I have 3 coming out, correct? Okay. So I total is equal to V over R total. V was 9 volts, 63 over 37. 9 times 37 over 63, 37 over 7, I guess. This is 7. So that's my total current. So the total current coming through here, okay, is this. Not all of it's going to go through here. Some of it's going to go through here, some of it's going to go through here, some of it's going to go through here, right? So this is the total crux, or the real problem in solving this is how much goes through each one. Okay. So let's look at the first resistor. If we look at the first resistor, so we found I total to be 37 over 7, right? I know that the voltage drop across here, yes, sir?
Sorry for interrupting you. Can I steal Lauren for 2 seconds?
Okay.
We'll be right back.
Oh, 2 seconds is up.
Oh, have her yet.
I think it's fine.
So the voltage across here, okay, the voltage across here is 9 volts, right? So the voltage is 9 volts. And the resistance here is 3 volts, 3 here, right? So I1 is going to be equal to what? So this was 9 volts, right? It'd be 3 amps, right? So I have 3 amps going through here. Over here I have what? I2 is going to be equal to 9 volts over 7 ohms. So I have 9 over 7 amps. Over here I have what? I3 is going to be equal to 9 volts over 9 ohms, going to be 1 amp. Okay. If I add all these 3 together, what should I get? I should get this guy over here, right? Because this is the goings in. I have this amount going in right here, and I have these 3 coming out. That's if I add these together, what do I get? I get 4 plus 9 over 7. Correct? Which just happens to be the same thing here. Okay. So I have the same voltage across here. We talked about that. I have found, so the way to do it was finding the I total. In order to find the I total, I had to find the R total, right? We went through how to find that. Okay. So last but not least, let's look at the power consumption in the first resistor. The power consumption here is going to be what? V times I, right? And the current going through here was 3 amps. So it's going to be 9 times 3. P2 would be the same, 9 volts times I2, 9 over 7. Power consumption on the third one here is going to be 9 volts times the current was 1. So 9 watts. Oops. 81. These are all in watts. Okay. So that's basically the parallel circuit. And now let's go ahead and take a quick peek at the example 12.6. In example 12.6, what do you see there? Is that a series or a parallel circuit?
Oh,
Looks like it's a combo. It's like your combo meal, right?
is that efficient?
So it's kind of like you have a series. So if, let's look at it. You have a R1, which is in series, and then R2 and R3 are in parallel, right? So I have a volt, I have a battery coming through here, and then it goes to one node where it's going to go like this, where
If R1 breaks, do
Mhm.
R2 and R3 lose power?
What do you think?
Yes,
Why?
because it's a not parallel circuit, a series.
It's a series circuit, right? So this is the downfall of a series circuit, right? You get one break, the whole thing, there's no current flow. Because if this pops, right, or the line breaks or whatever, and this is what a fuse does, right? A fuse in your house. It pops when it's trying to draw too many amps, right? It'll pop and disconnect the current flow, therefore protecting whatever device it was hooked up to, right? Because if you didn't have that and you continue to do your hair dryer, I mean, you could do really bad things to yourself, right? Okay, so yes, so since it's a series, that's what's happening. And this is the good thing. The good thing about the parallel is that if one of them breaks, you're still going to be able to draw current through the other one. Okay. Okay. So the way to view this is you would go ahead and you can't make this a parallel one, right? Because it's series on its own. So you would make this into one, combine it into one, and then find the total current. Okay, in order to find a total current, I need the current flowing through here. But this guy here, I'm going to view this. I'm going to try to combine this into one, so it's going to actually look like this. Okay, so I have 3, 7, and 9 here. So this 3 will still stay the same. This guy over here, the R total of here is going to be what? Correct? Oops, I'm sorry. 1 over R, right? 1 over R is that. So I'm going to get what? I'm going to get this is 63 over 16. Our total is going to be 63 over 16. So this guy over here is going to be 63 over 16 ohms. This is this many ohms. Right now I can combine these two. It would be 3 plus 63 over that is going to be equal to 1648, 111. So that's going to be my total, added these two in series resistance, and the voltage was 9 volts. So now my I total is going to be, my current flow is going to be V over R. So it's going to be 9 times 16 over 111, 144 over 111. So 114 over 111 amps is going to come through here. I'm going to still get the 114 over 111, but when it comes to here, it's going to split. Some's going to go here, some's going to go over here. If I call this I2, I call this I3, which one's going to be bigger?
I2,
Why?
since they have the same voltage, if the R is smaller, wouldn't that make the I bigger?
Correct. So the more resistance you have, the less current is going to flow through there, right? Obviously, right? This presents 9 ohms worth of resistance. This is 7. So more is going to flow through here and less is going to flow through here. As a matter of fact, you can take this voltage, this amps, I can tell you that I2 is going to be equal to what? 16 over 9, I guess, right? Right?
Can't see what
Actually, let's not, I don't wanna. This was 9 volts, was it 9 volts? 9 volts?
Yeah.
Okay. So the voltage drop across here is gonna be what? The voltage drop is V is equal to IR, right? Right? I mean, so I get 144 over 111 current times that. That's the voltage drop, right? The rest is going to be dropped across here. And you can back out the current that way.
Where's the 144 from? Oh, I see.
Okay? Okay, so it is a bit complicated. Okay, so you have to kind of work yourself out a little bit here. Something like this, probably I won't put on a test, but I will put on a series and a parallel. You would expect to see that on the test. Okay, so there's 11 points, so we're done. This is what I wanted to cover.